Today we are going to talk about divisibility and data sufficiency put together. So I'm curious if that strikes fear into anyone's hearts, if anyone goes, no one wants to leave, if that's just what the doctor ordered. What do we think about this? Is when you see that combination, data sufficiency and divisibility in primes, anything come to mind? Oh, hey, Guy, how you doing? Tyler, it's been a while for you. All right. Okay. Well, that's what we're going to deal with. So curious about people's background with data sufficiency first off. I know a lot of folks who come to these have already been prepping for a while. So I'm curious if you could just put in your notes on this topic here. Tell me your comfort or familiarity with data sufficiency. And let's put that on a 1 to 10 scale, where 1, where you're like, never seen, 10, you know, you're best friends with it. And maybe a 2 or 3 is like, seen and hate. So where are we on that scale? Just go ahead and type in a 1 to 10 scale. How do you feel about data sufficiency? I see a lot of, okay. All right, some real range. Yeah, Guy, you're not afraid of data sufficiency at all, but I'm seeing some 1s. All right, so it's people who are just like, what is data sufficiency? To be blunt, I'm not going to spend a long time talking about how it works, but I'll give you the basic idea, which is you have a couple of statements, and you're supposed to figure out how they relate to the overall question that's being asked, if there's enough information to allow you to solve. So let me just show you a quick version of this. Let me give you the idea. So here's a public domain question because we made it up. And the idea here is simply, what do we need to solve this question? We're not going to do this question right now, but the idea is simply that you choose A if the first statement allows you to answer the question. So whatever question they're asking, the first statement works. You choose B if the second statement would work. You choose C if neither statement would work by itself, but if you can combine them. You choose D if each statement alone is sufficient, and E if statements 1 or 2 and 2 together still wouldn't be sufficient. In other words, if you can't answer the question at all. And if you're going, what do you mean sufficient? In other words, enough information to answer the question. So if you haven't ever seen this before, you may want to take a quick picture of the screen right now to get a sense of this, or pull up your GMAT official guide if you have that, or a strategy guide if you have that shows those statements laid out. Because we're going to just, when I do the problems, I'm just going to put up 1 and 2, and we're going to have to make do with that. However, there's a nice little shortcut we can use when we're doing a data sufficiency problem. Anytime I do a data sufficiency problem, one thing I will look at is how to narrow down the answers a little better. And so anytime I'm doing a data sufficiency problem, I will write down the following. AD, BCE. Some of you have seen this before, so again, I'm going to zip through it. With the idea that if the first statement works, A and D are the only possible answers, and if the first statement doesn't work, if it's not sufficient, then only B, C, and E are possible answers. So we can narrow down to 2 or 3 answers right there. And for some people, that right away will improve their accuracy. This is just making sure we're we're all in the same boat about that. Any questions about data sufficiency as a whole? I know that was a very sketchy introduction for those who are new to it. And I would recommend if you're watching this and you know, on YouTube and have not seen how to do data sufficiency problem, check on that before we do this, because this isn't a lesson on how to do data sufficiency. If you're participating live, I think you'll be able to follow along. It'll be all right. Any questions on that before we move forward? Okay, so I want to talk about a couple elements that we're going to deal with on a lot of the divisibility questions. And a lot of it comes down to dealing with factors and prime factors. Yeah, so someone was asking for a repeat on the ADBCE business. And the idea is simply that if I look at a question, put that other one up just for a second again. If I look at a question where I'm trying to assess which of these statements is sufficient. So this one, for instance, says, how many of the employees are senior managers? And I look at statement one, it says 80% were senior managers. And I say, well, that's 80%, but of what? I don't know of what. So that's not sufficient to answer the question. So I could kind of run down the answer choices. They'll always be there when you're not doing, you know, one from me or from the official guide. You know, if you're on the test, the answer choices will always be there. But I don't really want to read them by then. I could do it though. I could say, well, let's see. So this by itself was insufficient. It didn't tell me what I needed to know. So I can say, well, it's not A because that says statement one alone works. B says statement two, okay, I don't know about that yet. C says both together, well, maybe I could combine them, I don't know yet. D says each one alone, well, no, if this one doesn't work, then they don't each work. E says they don't work, okay, that could still be. So the idea is that if I write down A, D, B, C, E, I'm always gonna be able to make that decision. If statement one worked, if it was sufficient, then I keep AD. But if it's not sufficient, I cross off AD. That makes sense? So then from there, I could look at the second one and say, 64 were not senior managers. Okay, but how many were senior managers? By itself, without any other information, that's insufficient. So I would run down the line. Wow, that's really big. I would run down the line and go to the next part of this, which is BCE. I'd cross off B. And then from there, I'd say, oh, next choice, can I combine these? Well, if I know 64 were not senior managers and the other 80% were senior managers, and there's no other choice, right? Either you are a senior manager or you aren't. There could be things that aren't binary, like 64 were, you know, French and 80% were, you know, German, but who says everyone there is French or German, right? But either you're a senior manager or you're not. That's true for anybody, right? We're all either senior managers or not senior managers. So then I can say, oh, 64 must be the 20%. Oh, I can solve for that. The beautiful thing about data sufficiency is I don't actually have to do it. I don't care how many actual senior managers there are. I can just pick that, and my answer is C. So the ADBC is a really nice tool. So for those of you who are brand new to data sufficiency or have never seen this before, I hope this was worth the price of admission, the super expensive price of today's session, just by itself, of just saying, oh, yeah, I can use this to make my life simpler and have to think less explicitly about each answer choice. I've seen people who've been studying the GMAT for 6 months and they're still going, okay, so statement one is insufficient, so I could cross off, I don't want to have to think about this any more than if I see cars stopping ahead of me, I have to think about which pedal to press. So that one's the gas, and the gas, I think, makes the car accelerate and then, right, I crash. So I need to have that stuff just automatic and I don't have to think about it. Okay, great. So then, you know, some issues that come up with data sufficiency and divisibility. And the reason I'm testing these two together or bringing these up together is, first off, that number properties, which would be divisibility and primes, positives and negatives, odds and evens, those three especially, tend to get tested a lot with data sufficiency. And there's often sort of a yes/no thing. Either this is prime or it isn't. Either this is divisible by 5 or it's not. And since the GMAT just can't ask a regular yes/no question, there's no like true, false, multiple choice kind of questions. Maybe it'd be nice if there were. They can ask these in a data sufficiency format. They'll say, well, we want to ask you if, you know, X is divisible by 9, but we can't just ask that. So we'll have you figure out whether you can find out if X is divisible by 9. And that's where data sufficiency comes in. So a lot of this comes down to being able to break things into pieces, being able to break things down to their prime factors. So we want to be able to recognize a prime number when we see it. Nick, I have a question. I'll come back to that question in just a second. So being able to break things down is really important. So we need to know our prime numbers. Hopefully we know what a prime number is, right? It's a number that's not divisible by anything but itself in 1. What's our first prime number? Yeah, 2, and it's our only even prime, right? After that, they're all odds, because every other even number, 4, 6, 8, 10, 12, is divisible by 2, so it can't be prime. So I got 2, I got 3, 5, 7, and some people get in the habit of starting to running down odds, and they go 9, 11, whoops, not 99, 9, 11, 13, but wait a minute, one of those is not prime. Yeah, 9 is no good. Then I got 17, 19. You can recreate this anytime if you just take a moment to think about the ones that you know are not prime. If I'm running down this list, partly what I'm doing is, working from memory, but partly I can recreate it pretty easily because I go, all right, well, let's see. It's only odds. The evens I don't have to think about. 15 I know is 3 times 5. 21 is 3 times 7. 25 is 5 times 5. 27 is 9 times 3. Okay, so what are the ones that aren't? So we want to be able to do that, and we want to be able to break any number down into its requisite primes. Sometimes there are some cool tricks we can do with that. So fun trick would be, let's say I want to know how many factors, not prime factors, but how many factors does 360 have? So I could start by breaking it down to its primes. So where would be a good place to start? How would I start breaking 360 down? Yeah, if it has a 0 at the end, we know it's a multiple of 10, so that's usually a pretty direct way to break it down. There's no wrong way as long as you're not actually incorrect. Like I could have said 2 times 180 or 3 times 120. There's nothing wrong with any of those, and if we keep going, they'll all lead to the same thing. We know what 10 is. It's 2 and 5. Those are primes, so we stop there. 36 we know is 6 times 6. This will tell us the prime factors, but that doesn't automatically tell me the actual number of factors. And probably the most standard way someone would approach, if they say how many factors does 360 have, is do what we might call a list or a T, where they do something like this. Okay, I'm gonna have 1 and 360, and I'm gonna have 2 and 180. But the bigger the number is, the less appealing that gets. Plus, even for a smaller number, if we forget even 1, the whole thing's out the window, right? So we can keep going like this. It's not the end of the world. I could do this. You might feel comfortable doing this too. We'll keep going until we have either 2 of the same, or we've crossed over. You have some you get back around to 72 and 5, and oh, I've covered them all. But this is a lot of work, so let's stop that for a second and look at another way to do it. So Abir has written, okay, my total, breakdown is that 360 has, what is that, 3 2s, 2 3s, and a 5. So if I put those together, 2 to the 3, 3 to the 2, 5 to the 1, there's a little cute shortcut I can do. And this is, to be honest, I'm going in the kind of category of little tricks more than the center of everything you must know about the GMAT, but it's still cool enough that I want to look at it. Here's the trick. If I had something simple let's say I was trying to make a sandwich and I only had 2 choices. I could have white or wheat bread, and I could have veggies or no veggies. Okay, well then there's 4 sandwiches I can make. I could have white bread with veggies, white bread with no veggies, wheat bread with veggies, wheat bread with no veggies. That's a combinatorics problem. The idea is I have 2 choices for bread, 2 choices for veggies, 2 times 2 is 4. Well, I could do the same thing here. I could say, well, I could put, if I'm going to make a factor of 360, I can put in 5 or no 5. So can we agree that when I'm looking at assigning a 5 or not, that I have two choices? I have two ways I could decide to use the 5. I could multiply it in to make a factor, or I could not, yeah? So how many choices do I have as far as using 3s? How many ways could I arrange using 3s to make a factor? Well, I had two choices for 5. So for 3, since I have more 3s, I have a little bit more. Yeah, I've got 3 choices, right? So my two choices for 5 were to use 5 or no 5, right? But for 3s, I have 3 choices. And I have 3 choices because I could use 3, 3 to the 2, or no 3. In other words, if I'm making something out of 3s, I could use 1, both, or none, right? Just like if, I don't know, you're trying to figure out what you have in your kitchen to make dinner. You're like, well, I have 2 carrots, so I could use both of the carrots or one of the carrots, or I could just not put carrots. That's 3 choices I could make, right? And then you look at something else. Okay, I have zucchinis. I've got 9 zucchinis. So I have 10 choices. I could put all of them, 8 of them, 7, 6, 5, all the way down to 0. So anywhere from 9 to 0 zucchinis with 10 choices. So how many choices do I have for the 2s? 4 choices. Same kind of reasoning. I could do, 2 squared, 2 to the 3rd, or no 2s. If I put this together, I've got 4 choices times 3 choices times 2. This is combinatorics. It's 24 choices. So what's my shortcut? It's out here, folks. First, break the number down to primes raised to powers. Don't make it 6s or 9s or 8s, but 2, 3, 5, 7, that kind of thing. Add 1 to each power. Multiply those powers together. See how I did that? I just said, all right, I've got 2 to the 3rd. That's going to be 3 plus 1. And I've got 3 squared. That's going to be 2 plus 1. And I got 5 to the 1. That's going to be 1 plus 1. That's 24. So what if I wanted to do the total factors in 480? Take a moment to do that. When you think you have it, type it in. So Nick, you've got a factorization. Now see if you can find the total number of actual, not prime factors, but total factors. Some of you are saying it's the same. That's interesting. Any ideas why it would be the same? Why would it be the same with a different and quite a bit bigger number? Certainly can't be that every number of that size has 24 factors. No, it's not. It's a multiple of 10. It's not a power of 10, right? 24 and 480 have a 10 in them, but they're not a power of 10. So it's not about that. No, it's fine. We're just hypothesizing here, right? Well, let's look at it. If we break 480 down, it actually is not that different from 360, right? 480, they're both multiples of 120, by the way, right? They're both 10 times a multiple of 12. One just 3 times 12, and the other is 4 times 12. So what happens when we break this down? We can do the same thing of 10 and a 48. No, it's not a perfect square. Then 48, you could do, if you wanted, 4 times 12, if you want to do that. But I'm going to do instead, to show, because we had 6 times 6, now we're going to do 6 times 8. Okay, so it's very similar to the other one. Six, of course, breaks down the same as before, 2 and 3. 8, some of you will just recognize that 8 is 2 cubed, and there's nothing wrong with just doing that directly, but there's also nothing wrong with saying, hey, that's 2 times 4, and 4 is 2 times 2. So, you know, you do not have to write this all out just because, pretty as it is, you don't have to do this. So we can count up our 2's now. We can say, all right, let's see, I've got 1, 2, 3, 4, 5 2's instead of 3 2's, right? But I just have 1 3 instead of 2 3's, and I have 1 5. So now if I look at this, it's equal to, or it is equal to 2 to the 5th times 3 to the 1 times 5 to the 1. So let's make sure that our math works out here. So what should I do? I break them down to primes raised to powers. I add 1 to each power. And what do I get? I get 6 times 2 times 2. Look at that. 24 again. Weird, right? But you know, what's really going on? We're dropping in complexity in one place and increasing in the other. All right. Are we at peace with that? Well, was it just a coincidence? Partially, you could say yes. But what you can also see is that when you trade off, you know, one number of factors for another, you can see some interesting balances. Now, if you look at the change, you would expect it to be slightly different, because look what happened. We got 2 more 2's. We only lost 1 3. So it might expect it to be actually a larger number. But that's not always how it works with multiplication, because when I go from multiplying in a 4 to multiplying in a 6, but I go from multiplying in a 3 to multiplying in a 2, I'm just trading off factors. So, I mean, one way to look at it is a coincidence. The other way is that they're both very similar numbers that have a lot of the same factors. They're both multiples of 120. One's just 3 times 120, and one's 4 times 120. So we're losing some possibilities and gaining others. But that's the idea, and I just want to make sure that everyone knows how to do that. So that's something we might occasionally have to do to avoid, you know, running through these. And one thing you can do to make sure we're right is run through later and try doing the t and just confirming, right? We better be right, but that's a way to make sure this matches. But you can imagine that when you have a number of factors like 24, you probably don't want to write them all out, especially if they're not asking anything specific about them. All right, so now we're going to add in the data sufficiency part of things, which basically is where, you know, they're going to ask you a question formatted like this. If R and S are positive integers, is R over S an integer? So they're asking very often a yes/no question. And then they're giving you some statements that deal with that. So I'll give you all a moment to look at it. By the way, meanwhile, someone was asking, is there a way for some of the harder questions, can we heuristically see what the answer is likely to do without doing the math? That's actually really common in a couple senses. One is just kind of knowing what kind of information you seem to have and whether that's enough information without actually solving it for yourself. So it's kind of knowing when you have enough information and what's likely to be enough information. It's also suspecting a trap sometimes. There are questions where where, for instance, the answer choice C seems way too obvious. One statement seems to give you exactly one part of what you need, and the other statement seems to give you the other part. Or that if you put them together, you seem to know everything. And those are cases where I'm very nervous about picking C, and so I might come to suspect that I can solve without using both, and that pushes me in a direction. So that certainly happens. But let me have you try this question out. Again, I would encourage you, if you don't already do this, to write down A, D, B, C, E. For those of you who don't have the answer choices memorized, another mnemonic device you can use, a lot of people use. This isn't, to me, a great way to write down your work, but just to keep track of what you're doing, is 1, 2, TEN, 1, 2, 10. So first statement is only is sufficient. Second statement only is sufficient. Together, either or neither are not enough. So that'd be another way of remembering. But give this a try and then pull in when you think you have it. All right, let's see what we got. If you haven't got an answer at this point, maybe put your best guess here. Just type it into the chat. Curious what people are seeing. And we have a couple options of this kind of problem. One thing that drives people crazy on data sufficiency is it can start to feel very abstract or theoretical. Like I'm just supposed to know about these factors and prime factors and the combination and the ratio and stuff like that. So it's a lot of interpretation. What do they actually mean? And then how can I make it more concrete so I know what they're, so I can actually test this. So let me ask first, when they ask if R over S is an integer, when would that be true? And when wouldn't that be true? In other words, what are they really asking when they ask if R over S is an integer? So an integer means not a fraction or a decimal. So that could be, negative number, positive number, 0, just no fractions. Although here, if R and S are positive integers, then R over S won't be 0, and it won't be a negative, right? A whole number. But why would it be that R divided by S would be an integer or wouldn't be? What would cause that to happen? So if we're saying that we're trying to see if R over X is maybe 3 or 5 or 10 or 12 rather than 3/2 or 2/5 or something like that, when would that be? What would that tell us about R and S? Depends on whether it's a bigger number or not, to some extent. Although I could have a big number on top and a small number on the bottom and still not have an integer. Like if I had, say, 20 over 3, right? That's going to be, well, the risk of looking satanic, right? 6 point repeating 6, right? So that's not gonna get it. So the top would have to not be any smaller than the bottom, but it has to go unevenly, it has to be divisible. So they're really talking in code here. And that's really important to understand, that a lot of time the GMAT's talking in code. What they're really saying is, translation, Is R a multiple of S, right? Another way to say that would be, is S a factor of R? In other words, does S go into R? As you can imagine, if we had, say, 20 over 5, the answer would be yes. And if we had 20 over 7, the answer would be no, right? 5 goes into 20, 7 doesn't, right? So that's what they're wanting to know. We don't know that it's true. Remember, it's a question, right? We're wanting to know, is R a multiple of S? Is S a factor of R? So if we look at the statements, statement 1 tells us, well, every factor of S is also a factor of R. Well, that's interesting. 1 tells me that everything, every number that goes into S also goes into R. What does that tell us? What does that mean? Are they the same number? Not necessarily. Ramona, why not? What else could be happening? But how could R have more if every number that goes into S also goes into R? How would that work? Can you give me an example? Sometimes we just have to try numbers. So like, for instance, let's say that S is 10 and R is 10, right? Then that would certainly seem to be true, right? Every number that goes into S also goes into R. Yeah, sure. Now, how would that answer the question they asked? Would that give me a yes or a no to the question they initially asked? So it'd give me a yes because R over S would equal 1, and that would give me a yes, right? It is an integer. So my job is then to say, okay, can I get a no? The idea with data sufficiency is I'm saying, all right, I got a yes, can I get a no? So I'm going to say I could have a bigger number. So let's say S is still 10. Let's not vary anything we don't have to. What could R be that would still make this true? R could be 20. So is it still true that every factor of S is a factor of R? Let's see. S has factors of 1 and 10. Those go into 20. And 2 and 5. Those will go into 20. Right? But R also has a factor of 20. That doesn't go into S, but that's okay. So then we're getting, okay, R over S is 2. That's still a yes. Okay. So then the question is, all right, well, that was interesting. It was a nice case, but it didn't change anything, so I didn't really need it, right? Tyler's saying if every factor of S is the same as R, then reduced it will still be an integer. It sounds like it. Try it with an odd number like what, Ramona? Maddie is asking, how do you pick the right numbers to get a no? And that is the $1 million question, right? Because the problem is we could sit there all day going, well, what about this? You know, but we want to think, what would the exception be, right? You know, imagine that I said, I'm thinking of a kind of animal, and I'm specifically thinking of a mammal. So does it lay eggs, right? And if they're going, well, let's see, bats, they don't lay eggs. Lions, they don't lay eggs. Humans don't lay eggs, you know. Wolves don't lay eggs, right? You could be there all day. You have to kind of go, wait a minute. Yeah, you know, whales, they don't lay eggs, right? You have to go, wait a minute. Is there a mammal that lays eggs? Oh, right, the weird ones, platypus and echidna, right? Those are the two. That's it. And if you don't know about that, you're not gonna get that one right, right? unless you're lucky and you think that, foxes do lay eggs and 2 wrongs make it right that time, right? So we have to kind of look for those exceptions. Where would something strange happen? So what about a prime, right? What if I make S prime? Okay, so let's say S is 7. So all of S's factors are really easy to list, 1 and 7. So if it has to be that every factor of S is also a factor of R has to be 7 times something, right? R has to be 7 times, we can call it, I need a question mark, N, right? So if I take that number, is it going to be an integer? It's going to have to be, because imagine I have, just to make it look less obscure, I won't call it question mark, I'll call it X, because it might make folks more comfortable. Say R has 7 in it, but it may have something else. That something else may be nothing, it may be 1, but it's something else. So then I say, okay, R over S would just be 7x over 7, which would be X. And if we say, all right, well, the only way that R could have a factor is if I multiply by an integer. I can't have, I can't have R be like 10.5 or something like that, right? That's not an integer, and it wouldn't then have 7 as a factor. So then I'm gonna have to say, all right, that's still an integer. So if there's something else that goes into R, then it'll be left over when I divide by 7. Does that make sense? In other words, if R has to have all of S in it, then when I divide S out, what's going to be left? Only any extra things that R has. But those extra things have to be integer. If I just knew that R was bigger than S, I wouldn't know that, because 10 divided by 7, of course, isn't an integer at all, right? Or 12 divided by 7. But if R is basically 7 times something, so we could just generalize that and say that S, we have 2 numbers. We have S, and then we have R, which equals to S times X, with X being something that makes it a multiple. X could be 1, 2, 3, anything I want, a billion, right? But the trick is that multiplying extra numbers in, and this is a really important point about divisibility, multiplying more numbers in doesn't stop something from being divisible, right? If you have an even number of fingers, you have 10 fingers, right? And then those fingers all multiplied. Each of your fingers, it sounds creepy, bad dream, each of your fingers turned into 3 fingers. Now you got 30 fingers. It's still a multiple of 10. And no matter what you multiply, take 30 and multiply by 7, by 17, by 29,000, by whatever, it's still going to be even, because it still has that 2 in there. And so if I take a multiple of 7 and keep multiplying more stuff in, it's still a multiple of 7. So one quick way we could see this without testing numbers, more theoretical, would just be to say what I think someone said at the beginning, which was to basically R can be bigger, but it has to have what S has, right? So if we recognize that what this basically tells us is every number that goes into S goes into R. R may have extra, but it will just be more factors, right? And that'll create an integer. So our answer is always going to be a yes. So the question is, how do we know this? Well, partly it's just doing the theory and making sense of it. It's also trying numbers and seeing if you can shake it loose. And one way we sometimes describe it is this way. We'll tell people when you're doing data sufficiency, you try to prove insufficient. So you don't say something's insufficient unless you can get a yes and a no. But you sometimes have to guess sufficient. You keep getting a yes and you go, well, I'm not seeing an exception, right? So what if someone said, does every country in South America have the same official language? I hope we all know the answer to that, right? But let's say I looked at several countries in South America and I go Spanish, 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 Spanish. Well, so far it seems like yes, they all have the same official language, Spanish, right? But I would actively look and say, can I find another? And I wouldn't say it's insufficient. I wouldn't say, it's probably insufficient. I'd look and I'd say, oh, look at Brazil. They speak Portuguese. Oh, there we go. Different language, insufficient now. But if I keep getting Spanish, 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 I would say at some point, well, I'm not finding any, so I'll have to guess sufficient. In that case, of course, I'd be wrong, but that's what we have to be really good at looking for those outliers, looking for those exceptions. So we're trying to prove, Disha, is that we're trying to knock them not as incorrect. They're always, the statements 1 and 2 are always true. We're trying to disprove the idea that they're sufficient. So if I can't do it, if everything I get gets me a yes, then I have to keep statement 1 and say, all right, it's sufficient. A, D are in, B, C, and E are out, right? So this one's sufficient because no matter what I do, I always get the same answer. Does that make sense? And then you ask if S was 10 and R was 7, that wouldn't follow the rules, right? Because if S is 10, if S is if S is 10 and R was 7, or for that matter the other way around, that then no longer fits, right? Doesn't fit the rule for this statement, because the rule for the statement says that every number that goes into S has to go into R, and none of the factors of 10 except for 1 go into R. 2 doesn't go into R, 5 doesn't go into R, 10 doesn't go into R. So if that's the case, I don't say, ooh, that's insufficient. I say, oh, I can't use these numbers, right? It would be like if I was trying to prove that there's more than one official language in South America by saying, well, you know, in Singapore, they don't speak Spanish. And you go, well, but that doesn't count. Singapore's not in South America. Oh, right, never mind that, right? So we have to go with one that fits the information we have. The 1, 2, 10 question, yeah, first statement only, second statement only, together only, either one works, or neither are not enough. The important thing about C, together, is that I would only do that if they don't work individually. Imagine if I showed up at your job and asked to be paid because together we were getting your job done. And you might say, Dmitry, I've never seen you at my work until now. What do you mean together we're getting the job done? I'm like, well, your job's getting done, right? Well, then I want to get paid. Together we're sufficient. And you'll say, but I don't need you, right? I can get the job done by myself. Go away, Dmitry, right? And so I don't want to take credit for something. So we don't want to combine just because, right? If I know statement 1, but I also know that, you know, R is even, well, I didn't need that part, so I wouldn't call it C. I'm only going to call it C if I need both statements to get there. Okay. So at this point, I wouldn't pick C anyway, because statement 1 was sufficient. So now I go to statement 2 and I say every prime factor of S is also a prime factor of R. So this says that they share prime factors. So now my question is, I could do the same thing, right? And in fact, a lot of cases, that's what I'll do. I'll reuse. I can say, all right, so S, you know, what I could say this way, R has all the prime factors that S has. So then the question would be, all right, well, it seems like I could just do the same one then. I could say S is 10, R is 10, and I already got R over S is yes, because we've done this. R over S is 1, I mean. And so I'd get a yes. So I have that done. I don't need to redo that. So now I'd think, how can I get a no? Did anyone, I saw some of you were A on this and some were D. So those of you who got A, did you find a way to have R not be a multiple of S? Yeah, Abhi, you're saying S could have a higher power of prime factor. So for instance, what if I said this? Could I have S be 16 and R be 2? Would that fit what we said? Is it true now that every prime factor of S is also a prime factor of R? This is a sneaky thing, right? Now, obviously R doesn't have as many 2's as S, but if I said, what are the prime factors, not the prime factorization, but prime factors of S, they'd just be 2. And what are the prime factors of R? 2. So R has all the same prime factors as S, but S doesn't go into R anymore, right? So now I have R over S, not an integer, it's 1/8, that's a no. And for this reason, this statement is insufficient. And if it's insufficient, then I can't pick A, I can't pick D, I have to pick A. Okay, so this is a bit of a trick. This is an official GMAT question, by the way. I don't think I showed that, but this is from MBA.com. What they're doing is a little bit of trickery, because if we're counting the numbers in the prime factorization like we did earlier, how many 2's, how many 3's, then of course this wouldn't fly, right? But if they say every prime factor is also a prime factor, then it's just saying they have to, if S has a 2, R has to have a 2, but it doesn't tell us the number of them anymore. Well, see, that's a tricky thing. KB is saying, do I, when I say every, do I have to mean every single factor? So no, it's every prime factor. Every prime factor. And so prime factor is when we list prime factors of numbers, we don't list repeats. That's why when I put prime factors of S for 16, I just put 2. So to make that clear, I'll rewrite this. Prime factors of 16, 2. Prime factors of 2, 2. Right? In other words, when I list what are the primes that go into this number, there's just 1. Someone's asking, is this one of the easier questions? They may have a difficulty ranking for this on MBA.com. I don't recall it offhand, but a lot of folks missed this today. It has a bit of a sneaky trick to it. So I would say, easiness is all relative. If these concepts all make perfect sense to you, then this is gonna be one that you could do pretty quickly and you might solve it in 40 seconds or so. But if you're not clear on how the prime factorization works or how to test, then this is not so easy, right? Someone who finds this easy is gonna think about it this way. They're going to go, they're immediately going to say, oh, they're asking if S goes into R. Statement 1 says that R has all of S's factors. Oh, S has to go into R. Statement 2 says R has all of S's prime factors. But it doesn't say how many of each insufficient A. And they could get that done very quickly. So in that sense, it could be easy for the right person. Tyler, the answer is every factor of S is also a factor of R. Yeah, well, in other words, the answer is statement 1 is sufficient. That's why we pick A. Statement 1 is sufficient. Statement 2 is not sufficient. They're both true, but 1 is sufficient and 2 doesn't fly, right? It doesn't answer the question for us. That makes sense? All right, let's see if we can knock out a couple more questions here. Pick up the pace a little bit now that we are more comfortable with data sufficiency, perhaps. This one's one of ours, but it's an interesting one, I think. Give this a try. Type in your answer when you got it. I'm not going to give you a very long time, by the way. Not sure, go ahead and pull this in, give it a shot. By pull, I just mean type in what you think it is. So far, no one's got this one. Bit sneaky. Okay, so different tries on answers, yeah. Okay, all right, all right, yeah, so this is not as affirmative as we like. First thing, I've messed with the wording a little bit just to show you that these all mean the same thing. So when I say divisible by, or a multiple of, or divided by it as an integer, those all mean the same thing. So the question's asking if 108 goes into N. Statement 1 is telling us that 12 goes into N, and statement 2 is telling us that 9 goes into N. So first, let's make sure we can agree on what's not it. So if we look at our ADBCE this time, they want to know if 108 goes into N. Now, statement 1 tells me that 12 goes into N. So how would I test to see if that's sufficient? Okay. So I could have a multiple of 12 that is divisible by 108 or one that doesn't. I know I can definitely find the prime factors, and I'll come back to that in a second, Ted. But if I were testing numbers, I might decide not to do that. So I could just say, what's a multiple of 12 that would be divisible by 108, and what's a multiple of 12 that wouldn't? So for instance, if I make N 144, then that would be a no. 144 doesn't the 108 doesn't divide into 144, right? What would give me a yes? In other words, what's a value of n, a multiple of 12, that might give me a yes, that might say, yeah, it is divisible by 108? It's got to be carefully, guys. It's got to be a multiple of 12. So your multiples of 12, if it's positive, if it weren't positive, it could be 0, which is fun. Would be multiples of 12 are 12, 24, 36, 48. Not factors, but the things that are built of 108s. So I'm seeing a lot of 216s. Now I think a lot of you are going to 216, which is not wrong, because we're thinking of a multiple as having to be bigger than the number. But it could also just be 108, right? So n is 216 would give us a yes. And as soon as we have a yes and a no, we know this statement is insufficient. It doesn't mean it's not true. It means it doesn't give us enough to get an answer. If you like something simpler, whoa, 1296, that's heavy duty. But we don't need anything so big. We could also just have said, hey, what if n's 12? Well, that would give me a no. It would be a multiple of 12, of course, but not a multiple of 108. And what if n's 108? That would give me a yes, of course. So I don't need to go fancy. I don't need to go big at all. There's no extra points for doing that. So I don't need all 4 of these, but any of those pairs will give me yes and no. So what answers do I cross off? Yep. It was just the question and the 2 statements are all phrased to say the same kind of thing, which is this thing goes into n, or in the form of the question, does this thing go into n? So yeah, we'd get rid of a and d. Okay, great. So now I'm trying to test statement 2. Statement 2 is the exact same deal, but it just tells me n's a multiple of 9. So if knowing that n's a multiple of 12 isn't going to prove that it's a multiple of 108, is knowing it's a multiple of 9 going to do it? Seems like I could do the same thing, couldn't I? Is 108 a multiple of 9? Yeah, 108 is 9 times 12, which might give us an interesting thought about statements 1 and 2 together. But if I go to statement 2, I could say, all right, well, n could be 9, and that would give me a no, or n could be 108. So don't feel too much need to be super clever and creative with your numbers. As long as you can get a no and a yes, that's all we care about. This is insufficient. So ideally, we'd be pretty quick to do that and get down to 2 choices, C or E. Okay, any questions about what we have so far? Be careful. Some people will go backwards on this, and a lot of people will choose D on this. And here's what I think, and tell me if you encounter this, maybe this mirrors what you're thinking. A lot of people choose D because I'll say, statement 1, yeah, 12 goes into 108, cool. Statement 2, 9 goes into 108. But that's backwards. We're not saying, hey, n is a multiple of 108. Is it a multiple of 12? In which case, yes. We're saying, hey, n's a multiple of 12. Is it a multiple of 108? So we've got to watch our direction, right? And that's really important, right? Or think about my South America example. If I say, hey, Dmitry is in South America, is he in Brazil? Is he in Argentina? You don't know. But if I go the other way and say, hey, Dimitri's in Argentina, is he in South America? Yeah, sure, right? So I've got to watch the directionality. If I know it's a multiple of 108, I know it's a multiple of 12. But if I know it's a multiple of 12, that doesn't tell me it's a multiple of 108. So now what happens when I put 1 and 2 together? Can I then tell, hey, 9 and 12 make 108 sufficient? What do you think? Can I choose C at this point? It makes me a little nervous just because all I did is use my times tables. I just say, hey, 9 times 12. It makes me just a little nervous. So it certainly could be, right? If n is a multiple of 12 and n's a multiple of 9, which is what the statements are telling us, then n could be 108, and that would definitely give me a yes. Tyler, I'm not sure what you mean about doesn't have to be true across the board. Okay, so 36, a lot of you are saying, well, what if n's 36, right? How did you come up with 36? That'll do it. And that kills this one off, and we have to choose the least satisfying answer. Yeah, okay, Tyler, exactly. Yeah, in different scenarios. So it can't just be that one case. I think what a lot of people will do is say, hey, 12 here, 9 there. Now, if I knew, let's say the question were something slightly different. Let's say it asked, is XY a multiple of 108? And statement 1 said, X is a multiple of 12. And statement 2 said, Y is a multiple of 9. What would the answer to that question be? What would we have that for that? No, it wouldn't be D. That would be the same backwards thing I was talking about. You can't say, hey, 12 goes into 108, 9 goes into 108. We need 108, and just knowing X is a multiple of 12 doesn't tell me, because let's say X is a multiple of 12 and Y is 1. Well, then I would just have X, Y is 12. It would be C. This would be C, because if I know that X provides a 12 and Y provides a 9, then when I throw those together, I've got it all. I've got 12 and 9 put together. JJ, does that make sense? Do you see why we want C there? All right, cool. So the difference here is it's all from the same thing. And how do we know we have them at the same time, right? In other words, I've got, and this gets down to what Ted was saying about factoring these down. What's my prime factorization of 12? What are the primes in 12? 2, 2, 3. All right, and the primes in 9? 3 and 3. So what do I know that I have? Well, to get a prime factorization, I take the most I see at any one time, right? So I'd say, all right, well, if I know that I have a multiple of 12, then I know it has to have 2 2s, and I know it has to have a 3. Then when I get to statement 2, I say, oh, well, I know it has to have 2 3s. Well, I already knew it had 1 3. Does that mean it has 3 3s? No, it doesn't. I knew it had to have a 3, and now I know it has to have 2 3s, but I don't know that it has to have all of that. So, and we can prove it by testing. 9 times 4 is 36. Does 36 divide 12? Divide by 12? Yeah, sure. Does it divide by 9? Yeah, sure. Oh, yep, 36 works. And so that's the idea of least common multiple. 36 is the least common multiple of a positive number, right? Is the least common multiple of 12 and 9. We don't have to go to 108. Imagine also that it had said, here's another variation. What if it had said, is X a multiple of 15? Statement 1 had said X is a multiple of 5. Statement 2 had said X is a multiple of 6. All right. Well, to have 15, I just need 3 times 5, right? This one gives me the 5. This one gives me 2 times 3. The 2 is irrelevant. It's just a distraction. And I say, oh, I've got a 5 here. I got a 3 here. There's my 3 times 5. My answer would be C again, right? I don't care about the 2. The 2 doesn't stop it from being a multiple, right? So that would be C again, because even though I'm pulling from X both times, there's no overlap between 5 and 6, right? So it doesn't matter that I have to find the least common multiple, because the least common multiple of those things is still a multiple of 15. However, in this one, the trick was that it wasn't. So it's good to be able to find least common multiple. And I can do that even with something a little more obnoxious. Let me show you here. Imagine, and they probably wouldn't ask you exactly this, but let's say I had to find the least common multiple of all these numbers, 9, 10, 12, 15, 16, 18, 20, 24, right? That seems, oh, I have to put it up. That would seem really prohibitive. Like, who has time for this? What can I do to save myself some time? Obviously, you don't want to multiply these all together. That would be a multiple, but it wouldn't be the least common multiple. What can I do? Well, the beautiful thing is these, yeah, I can prime factor them. And I might even notice that some of them are unnecessary. For instance, if I notice that, hey, 10 is a multiple of 30. So not a multiple, sorry, a factor of 30. 30 is a multiple of 10. So if I know it's a multiple of 30, I already know it's a multiple of 10. If I know it's a multiple of 18 and 27, I already know it's a multiple of 9. If I know it's a multiple of 24, I already know it's a multiple of 12. If I know it's a multiple of 30, I already know it's a multiple of 15. So some of these are kind of redundant, yeah? And then what I'm really just looking for is what's the most primes I'd ever see at a time, right? Beautiful, yeah, I think so too. Glad you agree, right? What's the most I see at any one time? So I could certainly write these all out. But I could also just kind of run through and say, all right, well, let's see, where am I going to see a lot of 2s? So my powers of 2 are 2, 4, 8, 16, 32. Well, 32 is bigger than anything I have here. So the biggest power of 2 I'm going to see is 16. I don't have to look for 2s anywhere else. I don't care that 2 goes into 24 or 25 or 27 because my powers go 2, 4, 8, 16. Anything that's more than 16 would have to be 32 or higher to have extra 2s, and that's not on my list. So there's all my 2s. Where am I going to see the most 3s? Which of these numbers has the most 3s? Yeah, try the 27. And to have more 3s, again, I would have to have the next power of 3, which is 81. I don't have that, right? Where am I going to see the most 5s? 25, and my next power would be 125. I don't have that, of course. And then there's no other primes. And that's the beautiful thing is everything's made of a lot of the same ingredients. It's like you notice a lot of foods are made of the same few things, you know, fat, oil, whatever, like wheat, soybean oil, corn, these certain things that get used over and over again, right? And 2s, 3s, and 5s will make a lot of the common numbers. Obviously, there are other primes. I could have thrown 14 and made us use a 7. I could have thrown in 22 and made us use an 11. I didn't. And so we have all these numbers, but they're made of these parts. So I know that the least common multiple is just going to be the most I see at one time of any of these numbers. So it's going to be 2 to the 4th times 3 cubed times 5 squared. I didn't need to necessarily do these all out, right? If I recognize that, because I could say, hey, 20 is, I already know about 10, it just puts another 2, but I'm good on 2s. If I want to do this conveniently, how could I, other than saying, okay, what's 16 times 27 times 25, how could I quickly do some of this multiplication? Any ideas of a trick? Yeah, I can group 2s and 5s to make 10s, right? So if I know that like 2 squared and 2 and 5 squared will be 10 times 10 or 100, then I can take another 2 squared and 3 cubed. I'm writing kind of sloppy here, but okay. So I'll have 100 times 4 times 27. Then I can do 27 times 4. I want to say on my fingers, although I'm not really using my fingers, I'm just using it to keep track. I'm saying, okay, double of 27 is 54. Double of 54 is 108. Hey, there's 108 again, magic number, right? And so that's 100 times 108. To multiply by 100, I just put 2 zeros on the end. So there's my answer. Would the GMAT ask you for something so large? Probably not. But if you can handle this, you can handle anything. So another little divisibility trick. And this will come up in a lot of data sufficiency contexts where I'm trying to say, hey, I know this information. I know this information. Do I know this other thing? All right. Well, that's all the time I've got for today. I hope you all found this helpful. And I will take a moment to ask any takeaways you have from today, any things you want to remember? If you take the class to get the hard copy guides, yeah, you can ship the guides to you, or you can get ebooks of them. C-trap, definitely watch out for that. Yeah, definitely a big one. It's so easy to get caught up in like, hey, that would be sufficient, but is it too good to be true? It's like if let's say they're asking you, you have to go to London on a business trip. Which of these will be sufficient? And one of them is going to give you first class tickets, and the other is going to give you a luxury hotel, and you're like, hey, put together that would be great, right? But do I have to have that much? Right? And a lot of times we're going with what makes us comfortable with what we actually need. Reinterpret, really, really important. Yeah. What other questions were? Combinatorics and probability, remainders. Remainders tie in with divisibility a lot. Combinatorics and probability, not so much. My biggest advice on combinatorics and probability is that for most people, just don't do it. You can get a 700 plus and not know how to do that. In fact, I talked to a student who got a perfect 51 on his quant score and honestly did not know how to do combinatorics. So it's not that it's so much harder. It's not like some kind of bizarre topology or something like that. It's simply that there's so much else to be tested that I wouldn't make that a high priority. But other than that, there's some decent material in the official guide, or you can seek out some third-party resources. We have a section on it in our number properties guide, and I know some other companies will have, like if they have books of problems, they'll have a set of good combinatorics and probability problems. I always recommend the good free stuff on Khan Academy as well. Yeah, so factorization, prime factorization is really important. One thing we didn't have time for today was the connection with consecutives, knowing that, for instance, if I have six numbers in a row, they're going to be divisible by 6 factorial, all the numbers down, 6, 5, 4, 3, 2, 1. There has to be one of everything. Just like if I have 7 days in a row, there has to be one of every day of the week. Guessing, I mean, you always want to move on by around 2 minutes. So using your ADBCE to narrow the answers down, and then if you're stuck, guess from what you have. But the general idea would be, unless you can prove insufficiency, figure what you have is sufficient and go with it. All right, other questions? Someone was asking about the frequency of our free pep hours. We offer about 1 a month, I believe now, sometimes 2. And the previous ones are all available on YouTube, and they vary in their topics quite a bit. We try to mix up quant and verbal. Someone's asking, is there a way to use quant thought process for verbal? I could talk about that all day in a way, but it's a tough question to answer quickly. The one thing I'll say about that is that a lot of people think of verbal as totally different, like it's just a matter of opinion, and it's really not. So I will say that the answers are often provable, just like they are in quant, not in the same way, not from like first principles necessarily, but on verbal, I do want to be able to say this is wrong because, and here's where the support is. So when you're looking at, say, an inference question, where is the actual support? How can I prove that this can be inferred? It's not about opinion or guesswork. Yeah, you have your yellow laminated pad for scratch paper for both quant and verbal. All right, folks. Well, thanks so much for your participation. I was glad to have an active, lively group today. Hope you found this helpful. If you're watching at home, hope you enjoyed too. Get in touch with us if you need anything. If you want to take a where'd it go? If you want to take a class, here we go. There's where you can go to check out upcoming classes. All right, everybody. Have a great night.